Greetings everyone, it's Professor Fiore, and in this video we are going to take a look at the low frequency response of a JFET voltage follower, in other words a common drain amplifier. One of these. So here we have a small signal FET, a 2N5458. Now the configuration that I have here is a self-bias. We have a 2K ohm resistor out here in the source, and this is similar to the circuit that we used in the basic common gate video. So the bias is essentially going to be the same. This is a self-bias. The specs are down here. The GM0 is a little over 3 millisiemens. The VGS off is almost -3 volts. And we get about 4.5 milliamps for the IDSS. Now I'm going to run through the bias here fairly quickly. If you want some detail, I suggest you go back and look at that other video. Here, I just want to kind of get through this because we're going to need some parameters like the GM value. All right. But basically, this is a standard follower. We have an input voltage generator back here going into the gate of the FET, output taken off the source of the FET. So followers, their whole idea is a buffer. They don't produce voltage gain per se, but they prevent loss, right? That's the big deal with them. So non-inverting, right? Input phase and output phase are identical, present a very high input impedance. And, real quick, just looking at this, that the RG value here, the 2 meg, is pretty much going to set the input impedance of this particular amplifier. All right. So if we go through the analysis on this, and I'm just going to bring this up here, right? Again, this is in that other video, but very quickly, because it is self-bias, we can use a self-bias graph from the text. GM0, right, the 3.17 millisiemens times the RS, the DC value, which is right here, the 2K. Multiply that out, 6.34 from the self-bias graph. You would get the ID-IDSS ratio, which is 18%. So we can multiply through and find out what the current is, which will be about 0.8 milliamps. But we also know that GM is equal to GM0 times the square root of that ratio. So when we crank through that, we get the GM, which is what we really need, 1.35 millisiemens. Knowing that, we can find the gain of the amplifier, right? Like I said, should be a little bit less than 1, but that's GMRS over 1 plus GMRS. So we know the GM is 1.35 millisiemens. RS in this case is the AC value seen off the source, which is 2K in parallel at 12K or 1.7K. So when you grind this out, you're going to get a gain of about 0.7 or -3 dB, right? So the output's going to be about 3 dB less than the input. All right, so that's all, the background. We can check that real quick. We could do a DC analysis, for example. I just want to verify, do a little sanity check. I think this is always a good thing to do. All right. So, you can come over here and, like look at, for example, is my gate, right around 0 volts, which it should be for DC. And in fact, all right, there it is. It's just about 24 microvolts. Okay, looking good. What do we have on the source resistor? Well, about 1.6 volts. And, sure enough, there's a little over 800 microamps. So, this approximation that I threw out there at about 0.8 of a mil, that's looking good. We can verify the AC performance, the mid-band performance, right? We could, for example, do a transient analysis. Just look at a couple cycles of the waveform over here. Start at 1 millisecond, go to 3 milliseconds. See what we get. And I'll expand this out so we can see it a little bit better. Put the legend on here. So the generator is the green signal. We set that up to 100 millivolts peak. And the load is the maroon signal. So you can see, yeah, we are losing some signal there. This would be 75 millivolts right here. So we're a little bit less than that. Probably just a little bit less than what the calculation is. But it's in phase. It looks the way it should. All right. So now let's move along to, the interesting part. The lead network analysis, right? The new stuff, yay. What's happening on the low frequency end? Well, if you've seen any of the other videos on lead network response for amplifiers, you know that the lead networks are created by the coupling capacitors and bypass caps. Well, in this case, there is no bypass cap, but we do have an input coupling cap and an output coupling cap. And before we really get into it, I would like to point out that on an amplifier like this, you might be able to get away without an input coupling cap. You know, I just indicated that the DC value out here was measured in tens of microvolts. So as long as the generator, the source back here, isn't producing its own DC value and is not, you know, harmed in any way with a very, very, very small DC voltage, and it probably won't be, you know, in most cases, you could even dispense with Cin. You could just run this straight in, right? Now you couldn't do that if you had some kind of like voltage divider bias or something where the, you know, the gate over here, or if you had a bipolar, the base wasn't sitting right at ground. In this case, you could though, right? Most likely you could. But just to show you how it is done, right, I've thrown in this input coupling cap, 100 nanofarad. On the output end, you know, we verified that the source of the FET is not at 0. You know, it was about 1.6 volts. So I want to block that 1.6 volts DC from getting to the load. You know, that can be a big problem. And certainly if this cap wasn't here, you know, this load would affect the bias as well. So we definitely need an output cap here. And this is going to create another critical frequency. So I've got two of these. And again, because we're looking at the low frequency response, we want to see which one of these two affects midband response first, right? That's the dominant one. And as usual, we'll define that in terms of the 3 dB down point. So what we need to do now is look at some equivalent circuits, right? So we have an input network and we have an output network. So let's take a look at the equivalents. All right, so on the input end, here's the generator, 50 ohm generator internal impedance. There's the cap. Here's the 2 meg biasing resistor we had on the gate. And then I just have a resistor over here which represents the Z-in gate for the FET. Now I've just thrown down, you know, a very large value of, you know, 1 gigaohm. But, you know, at the frequencies we're looking at, and depending on the FET, it could actually be a lot bigger than that. You could have 10 to the 12th ohms here. All right? It's huge, right? It's huge, Charlie. It's huge. So finding out the value, the effective resistance value for the cap, is a fairly straightforward process. This is easier than, you know, doing the bipolars, right? You know, in the bipolar case, you got to look at Z and base, and there's beta, and there's all that business, R prime E. Here, it's just, oh, Z and gate, yeah, huge, done. Because huge in parallel with even 2 meg is just whatever that resistor is, 2 meg, right? You put 2 meg in parallel with 1 gigaohm, and it's basically 2 meg. Now we just look around the cap, right? You're going to Thevenize around the cap, basically a superposition thing where you short out your voltage source, your VGen, and what we end up with is 50 ohms off to the left going down to the ground. And from the ground back, we would have this combo, which is about 2 meg. Right? Well, you know, what's 50 ohms out of 2 meg? All right, that whole thing is 2 meg. Done. All right, so we know we've got 100 nanofarads, we've got 2 meg. Plug it into your universal critical frequency formula, see what you get. Moving over to the output end, right, just to remind you, right, here's the output end, RS and R load, 2K and 12K with a 1 mic cap. All right, so there's the 2K and the 12K, the 1 mic cap. We also have to figure out what is the impedance looking back into the source of the FET. Okay, in other words, we're sitting out here peering this way. Whatever this is, that winds up in parallel with RS. Well, you know, out this way, we've got the current source, which for the most part, we can ignore. It's big enough. Certainly way, 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 way bigger. Orders of magnitude bigger than 2K. So we can ignore that and just say, well, what do we see looking back this way? And from preceding work, we have discovered that that is equal to 1 over GM. Now, we know what the GM value is. Right? Again, take a look at that other video, 1.35 millisiemens. So take the reciprocal of that. That works out to 741 ohms. So we have sort of a mirror image of the first circuit, right? Again, you look around the cap, what do we have? On the left-hand side, we have these two in parallel, right? A 741 in parallel with a 2K. And then that winds up being in series with the 12K, right? Common error here is putting everything in parallel. No, 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 right? The cap is sitting here. I want to see what is it that the cap would charge and discharge through, right? Think of a simple DC circuit. and you're just trying to, let's say you've got a cap charged up and you're going to discharge it. What does it discharge through? So these are in series. So I've got 12K in series with this parallel combo. What do those numbers work out, right? Once I get that R and C, I plug it in the formula. What do those numbers work out to? Bingo! It's all done over here. So on the input end, like I said, 50 plus 2 meg in parallel with huge is 2 meg. 100 nanofarads, that works out to just about 0.8 hertz, right? A fraction of 1 hertz. On the output end, we're looking at the 741 in parallel with the 2K, all right? And then you add in the 12K. So this combo over here is about 541 ohms, plus the 12K, you're looking at, a little over 12.5K. Take your 1 mic, grind it through your formula, 12.7 hertz. Out of the two, clearly the output network is dominant. It's the higher frequency. It's the one that affects mid-band response first. So we expect this gain somewhere around minus 3 dB, okay? As it drops down in frequency, right, we want to see where does it drop down another 3 dB, whatever that worked out to. Maybe the gain's minus 4.2, let's say. I'll just throw a number out. Okay, so I'm at minus 4.2. I want to go to another minus 3 from that, so minus 7.2. See what the frequency there is. Hopefully it's all going to work out. We'll get somewhere around 12, 13 hertz. All right. This is far enough removed from the input lead network that there should be very little interaction. In other words, there should be very little loss caused by this network, the input network, down here at 12, 13 hertz. All right. Maybe a tenth of a dB or two. Go back to the original circuit and let's do a sim. Before I do that, I'll just put this up here as a little copy for us. All right. So this is what I just had combined all up on the other page. So let's go and do the Bode plot here. We'll do the AC analysis of the original circuit. So I'm going to go from a tenth of a hertz, 100 millihertz, up to 100 kilohertz. Well, as a matter of fact, let me increase the number of points on here a little bit so we can get a little bit more accuracy. And here's our graph. All right. So let's see what we have here. All right, so this is sitting at minus 3.3. We were expecting, like I said, somewhere around minus 3 dB. So that's looking good. Now I want to go 3 decibels down from that. So somewhere around minus 6.3. All right, that's going to be our half power point, basically. All right, our lower break frequency, the F1. So right around there, we're looking at 12.776. Okay, call it 12.8 hertz. All right, and I'll just sneak this up here. We calculated 12.7. All right, you can't really complain too much about that. All right, that's right on the money. Now, if you look carefully at this, you notice, look at this slope. This is the slope of that one network, right? The output network. And right around here, you can see it's starting to get steeper because this is where the input network is coming in, and that was at about 0.8 hertz. So here's 1 hertz right here. So right here is where you start to see the two networks, both the input and the output network, kicking in, right? So this should be like a 6 dB per octave roll-off. This would be around a 12 dB per octave roll-off. All right, now, how do we check that? Well, if you've been watching these videos, you know exactly how to do that. We can come in and alter capacitor values because in a lead network analysis, the cap is the only thing that affects the response sort of independent of everything else, right? In other words, if I change the value of C in or C out, it does not impact the bias, right? It's only going to impact, the critical frequency. Whereas if I, changed RS or R load or something like that, that's going to affect the gain. It's going to affect other things. So in the case of a lead network analysis, that's a really nice way of checking stuff. All right. So one thing, we could do is come in here with C in and drop this to a much smaller value. So it becomes the dominant network. So in other words, it leapfrogs over the 12.7. So if I were to decrease this by a factor of 100, right, make C smaller by a factor of 100, that would increase the critical frequency by a factor of 100. So from 0.8 hertz, we'd be going up to 80 hertz. All right. So at least that's what we would expect. Okay. Now, I will admit, and if you think about this for just a second, if you translate that up by a factor of 100 to 80-ish hertz, now it's not even a full decade between these two. So there probably will be a little bit of additional loss from the output network, maybe a few tenths of a dB. And in fact, that's going to shift the frequency just a smidge. Let's see just how far it goes. How much is a smidge? I don't know, more than a dash, I guess. All right, so do the same deal as we did before. So again, we're looking at about negative 3.3. So we want to go to about minus 6.3, somewhere around there. And we're getting, well, that's 81.8. If we went there, it's 80.6. All right, so somewhere in the, let's be conservative and call it 82 hertz. Okay, somewhere around there, 81, 82 hertz. All right, which, like I said, we kind of expected a little bit of added roll-off, right, from the output lead network. So that makes perfect sense. If we were maybe a little bit more aggressive with this, or we could also turn around and just make this bigger, right? We could make C out bigger, which would push this frequency down a little bit. But we're still getting very good agreement. All right, so we go back and we say, all right, we predicted initially 12.7. We came up with about 12.8. And with this shift, we come up with 82 instead of what should have been 80, right? You translate this back down by a factor of 100 to 8.2, right? So, or excuse me, 0.82. So that's looking really good. All right, so there you go. In many respects, this is a lot like the bipolar follower. We still have input and output caps that control things. Really, the difference is focusing on the FET itself, right? It's actually a lot easier, I think, dealing with the FET because the Z in gate is very easy to find rather than finding Z in base. And even finding the Z out of the source is easier to find than the Z out of the emitter, right, for a bipolar. So it's a little bit quicker, right? You can't complain about that, all right? Well, I guess you could, but, nobody's going to listen, all right? Okay, questions? Put them down in the comments section, and we'll see you next time. Have a good one.